All right, in this video, I'm going to go over section 5.3, higher order Taylor method. So the first one, we're going to study local truncation error. So why need to study this, and then why is this? Because from section 5.3, we're going to study several numerical methods for solving algebra problems, but we need to compare two. In order to compare them, we need to certain tool to measure the accuracy of each numerical method. So here, the 5.3, so you can see that we introduce a basic tool to measure the error called the local truncation error. So let's see, what's the definition of local truncation error? So for given difference method, okay, so the local truncation error is defined by tau. We use the symbol tau, okay, for truncation error at I plus 1 time step, okay, and then of h. So it means that this truncation error can be considered as a function of h at time step I plus 1. That is equal to difference between yi plus 1 and wi plus 1. You see that yi plus pi, that's actually the what? You can see, I think I missed the see h, okay, so there is h here. I missed the writing h right there. So yi plus h times pi, that's the wi plus 1 in difference method, right? So the difference between yi plus 1 and wi plus 1, actually that's the yi plus 1 is the exact value at times the I plus 1, and then the approximation obtained by difference method at I plus 1 times that. So divide by h, okay? So because h, so then we can take out the pi out of the fraction because there is h, okay? I missed the typing h. So this is a definition of truncation error, tau I plus 1 over h. So if you apply the I mean, for the Euler's method, local truncation error going to be y, what? Let's see, you can see that yi plus 1 minus yi over h minus f. Because here in Euler's method, the pi must be what f, right? Source term, the differential equation. So now here's note, the local truncation error give a local error because it measures the accuracy of the method at a specific step I plus 1 time step or I step, okay? So or I minus 1 step. Anyway, so for specific time step, the local truncation error give the accuracy, okay? So now and they're assuming that the method was exact at the previous step, okay? So now introduction to the BOH to the P, H to the P, to the P, okay? So what this? Yeah, we'll see. In chapter 5.2, we saw the Euler's method as this. I mean, this is Taylor expansion of the yi plus 1, right? So with degree 1, order 1, I mean. So, and this is Taylor polynomial centered at ti when t is equal to ti plus 1, okay? And then this is the last one term going to be remainder term. So then yi plus 1 minus y over h minus f, which is the truncation error, okay? Tau I plus 1 over h is going to be h over 2 times y, the secondary to y at cosine I. You see that here? Because you see that yi plus in a Taylor polynomial right there, yi plus h times f of ti yi. This is the what? See, that's going to be what? The we by the difference equation, yi will be replaced by wi. So yi plus 1 minus this one will be this, okay? So the now right here, oh, okay, and the second derivative y is bounded by m, then local truncation error is going to be bounded by h over 2 times m. So I told you, so m is a fixed it's a fixed number, right? So h is a parameter we can control, right? So local, then we can say the local truncation error is bounded by, bounded by h over 2 times m, but the local truncation error will be decreased linearly as h is decreased. Okay. So now then we can say the local truncation error in Euler's method is going to be big O h. The big O h is what means that the big O h means that a constant times h. You see that here 1 over 1/2 times m can be considered as a constant, right? It's a constant h. So what if we got the certain method that its truncation error is big O h square? It means that the local truncation error will be decreased quadratically as h is decreased. Okay, so now you see that here p, if p is increased, that means for certain for a numerical method, if the local truncation error for that is big O h to the pth power, if p is for example 3, 4, 5, 6, then means that what the local truncation error is decreased so I mean the faster than linear, faster than quadratic, okay, as p is increased, right? Okay, so p is if we develop a certain numerical method whose p is the certain big number, that means the numerical method will give us the really good accuracy, better accuracy than other numerical method whose the rate of the local truncation error is less than p. Okay, so let's see. So you see here, it means the local truncation error in all those methods get smaller linearly as h gets smaller. That's what I said. So if you develop a numerical method whose local truncation error is big O h squared, then it must that local truncation error is decreased quadratically as h decreases. So now the so when you develop the okay, here's a question: then how can you develop numerical method has higher order of h big O big O h to the pth power as your local truncation error? Then think about this: in Euler's method, we use a Taylor polynomial, right? So now we're gonna start from the Taylor's polynomial. Okay, so actually that's the name of that one is called Taylor method of order n. So in Euler's method, we just we construct the Taylor polynomial of degree order 1, right? But now here we construct the Taylor polynomial order n. Nth Taylor polynomial centered at ti and evaluate that t is equal to ti plus 1. We're going to get this, right? So now then, since y prime is f, the second derivative y is going to be f prime, and the case derivative y is going to be f k minus 1th derivative of f, right? Now then, so we're going to rewrite y I prime and the y double prime through the dy sub cosine I n plus 1. See here, y sub cosine I n plus 1, that's the that's one denote the n plus 1's derivative y at cosine I, the y of cosine I, okay? So for convenience, I just write, instead of writing this, I just put this one. So now then we got this one here. So Taylor method order n is obtained by deleting the remainder term. Can we delete it? Okay, and then the wi plus 1 is wi plus h times t of n. Okay, I mean n t, and let's just say tn. Okay, what's a tn? Tn is just h times fi through the second term from the last. Okay, so this. I mean, so we can simply saying that this is we can express this one using the sigma notation. Sigma j equals 1 through the n. This one h to the j minus 1 power over j factorial in the f of j minus 1's derivative of f. Okay. So then the Euler's method is Taylor's method of the order one. So you see that Euler's method is a specific case of Taylor's method. Okay. So now see, let's consider the following integral problems. All right, so find the difference equation using Taylor method of order 2, and then find the difference equation using Taylor method of order 4. Then, depending on the order, upon the order number order, we just, when you construct the Taylor's polynomial, then for the terms, the number of terms in Taylor polynomial will be determined, right? So here, to figure out the Taylor's method of order 2 and 4, we need to figure out the derivative of, first, second, third, right? Up to third derivative of f, right? So we find out f prime, f dot prime, f second derivative, f second derivative and f third derivative, right? And then we're gonna figure out t2 and t4. Okay, so we get this, and then we get that. So now, then we step 3 to derive the difference equation by substituting t2 and t4. Okay, so keep in mind this, the goal is to figure out the difference equation. Okay, so this is a difference equation of Taylor method of order 2. That's a difference equation of Taylor method of order 4. Okay, let's see. Now then, let's see right here. Yeah. Excuse me. So see theorem 5.12. The local truncation error of approximation obtained by Taylor method is big OH to the nth power. Okay. So why? Okay. So Taylor polynomial of order y. Keep in mind this. Why we developed Taylor method? Because we want to develop numerical method having higher order of h and b in a big OH, as the rate of local truncation error. Okay, so one of them is a Taylor polynomial, a Taylor's method. So in the theorem 5.12 says that the order of in the Taylor's method, order of the Taylor's method will determine the rate of local truncation error. Here writing n. Okay, here's n. So why? Because okay, so we start from the Taylor polynomial of y of t of order n. Okay, which is this, right? So now you see y we got f prime, right, through the n derivative of f, right? Because it was originally the y prime, y dot prime through the y to the n plus 1 prime. N plus 1 derivative y, right? But we replace the we express every single the y terms and their its derivatives in terms of f and its derivative. Okay. Anyway, so then we see yi plus 1 minus y. We just move the all of terms in the right hand side except for the remaining term to the left hand side. We got this. Now we divide by h. Then we get this. We see that here. This is what tau I plus 1. This is local truncation error. Right? The minus, you see pi. Okay. See. All right. So now, oh yeah, this is not tau I plus 1, but that is tau I plus 1, right? I'm sorry. The two terms in left hand side is a tau I plus 1. This is typo. Now this is equal to what? H to the nth power over n plus 1 factorial. Okay. So now see here we assume that y is in Cn plus 1 space. Okay. And then n plus 1 0 to y must be n 0 to f is bounded on a comma b. I think that's the assumption. Second. Yeah, it should be, this is the assumption. So now then what? The n 0 to f is bounded by a certain number, and the 1 over n plus 1 factorial is also a fixed number, right? So that number, this one is the value of this one term is is determined by what? Depends on the h, right? So tau I plus 1h is big O h to the nth power. Okay. So now this that's why truncation error, a Taylor method, is big O h to the nth power. So if you want to get the higher rate of truncation error in the Taylor method, then you need to increase the order of the Taylor. Okay, order of Taylor's polynomial in Taylor's method. Okay, so that's the main things in the theorem 5. Section 5.3. Okay, so let me stop here.